Well, this is the second of 3 videos on nucleophilic addition reactions. We've been looking at the carbonyl and attacking it with a nucleophile. Now, don't forget that in the nucleophilic acyl substitution reactions, we had a leaving group on one side of the carbonyl, but in the addition reactions, we have no leaving group. We have alkyl groups, or in this case, an alkyl group, and a hydrogen. We have an aldehyde. So ketones and aldehydes, we've looked at their reactivity in the first video with base conditions, Grignard reagent, cyanide, aluminum hydride, which is the more reactive hydride, and borohydride, which could be used in the presence of water. But in the first step, in those conditions, base conditions, we attacked with something negative. Came in, advanced the electrons up to the oxygen, and capped with a proton provided in a second separate reaction for these two here, the aluminum hydride and the Grignard reagent, aluminum hydride and Grignard reagent. We had to use a separate second reaction, a second day, so to speak, of reactions, wherein we'd cap with a proton. In the case of cyanide and borohydride, we had a proton source in the very same solution, a weak acid, that could protonate the oxygen to give us an addition product. In this video, what we'll be looking at is addition of strong acids, catalytic amounts of strong acids, so that we can add in water, alcohol, diols, and amines. These have less basicity than the nucleophiles up here, and so we have to kick them off with an acid. We have to kickstart the reaction using a small amount of acid. Now we will see as we close the video that amines really don't need, this one doesn't need an acid in the first step to protonate this oxygen, but these will. We'll see that. Let's go ahead and look at addition of water to our carbonyl in a ketone or an aldehyde. So if we had no catalyst, we'd have very slow reaction because water is not very nucleophilic, and thus we can't really propose easily an attack on this carbon here because it just doesn't have much basicity or polarizability. It's just blah. It doesn't have much reactivity at all. We can't propose the oxygen take a proton from the water. It's not very acidic. So it's neither very basic, it's not very acidic, so we just wouldn't have a very fast reaction to this product. But if we take and add a catalyst, either an acid or a base, we're going to look just mostly at acids and we'll see why later, but we could catalyze the reaction to form this diol by base or by acid. Let's look at the use of an acid. If we added a drop or so of HCl, we would allow that acid in water dissociate to H3O or hydronium ion, and we could certainly propose then more easily the protonation of this oxygen in the carbonyl, which would increase its reactivity. It would activate the electrophilic site in the carbonyl. This would be a more reactive carbon if the oxygen is protonated. That's in acid conditions. In base conditions, if we were to add a few drops of hydroxide, then the hydroxide would be more basic than the water, and it would be thus more nucleophilic, more inclined to make an attack on the carbon. We would have activated the nucleophilic site. Either way, we can catalyze the reaction so that we have the formation of that gem diol. This gem diol, this is called the geminal diol, meaning off the same carbon we have two OH groups off the same carbon. If it had been vicinal, it had been off of adjoining carbons. But this is a geminal diol. We can look at how we can make that more quickly now that we have acid conditions. A few drops of a strong acid. We can protonate to some small degree. Not every single one of these oxygens will absorb that catalytic amount of proton, but some have some interaction with the proton, and as soon as they do, we have an increased rate of reaction of the water with this carbon because it's right across from an oxygen that's positive. And remember, if I hurt, the oxygen's hurting, he's going to pull more strongly on everyone he's bonded to. So if I hurt, you hurt. This is, by resonance, going to share that positive charge. So we can draw the water in, and with loss of that catalytic proton back to solution, we can make our geminal diol. I'm going to draw it in a more obvious way that we're just going to switch these positions here. We would have, with the loss of the acidic proton, the catalytic proton, we would have our gem diol. Now that's looking at this reaction in acid conditions. We could also consider, again, a few drops of the base, hydroxide, into water. We could have the attack of the carbonyl without protonation. There's no proton to protonate this oxygen with. We're just saying base conditions. We could attack the carbon, have a negative charge on this oxygen, and then with the reformation of hydroxide by ripping off from a weak acid this proton in water, we could make the gem diol. So we can have acid catalyzed hydration of a ketone or base catalyzed hydration of a ketone. The gem diol is the hydration product. They call it a hydrate of the ketone because what you've done in the end is you've absorbed both an OH and an H. You've absorbed water into the ketone. You've added water. So it's called a hydrate of the ketone, a hydration reaction, or we can say an acid catalyzed hydration, base catalyzed hydration. But we need the catalyst. Now let's just focus on the acid conditions, because what we're going to do is go on from the gem diol-like structures and do more chemistry. Now this is very important. If we look at the gem diol at the point we are at the end of these catalyzed reactions, if we're in base conditions, the only thing this gem diol can do in base conditions is have the base come in and take a proton from one of these two OH groups. And what would happen then is we'd be going backwards. But we'll see if we're in acid conditions and we have a desire to have a good leaving group from one of these two OH groups, we can protonate. And that would give us a new oxygen as a leaving group. So if we attack with something other than water, in this step here, if we take something other than water, maybe something other than water, maybe something like an alcohol, and make something like the gem diol, we can protonate the oxygen in the carbonyl again. We can protonate it twice and create a good leaving group and have the potential for something new. We cannot really do anything in base conditions from the gem diol other than abstract a proton. We can't make a good leaving group. Alright, so let's look at acid conditions from here on out, where we're going to use something other than water to make that initial addition product. So what I'm going to go ahead and do is say, okay, if we had alcohol with the ketone and we had acid, I know I could protonate this carbonyl, and I know the the ROH could come in and attack, and we could make, just like we saw on the last slide, we could make something similar to our gem diol, wherein the only difference is, instead of an OH hanging off this carbon, we used an alcohol to attack this carbon. And we've taken and given the acidic proton back to solution. We've made something like a gem diol. So it's very, very similar to what we saw, and the pathway would be very similar to what we saw with the gem diol. We still protonated this oxygen. We'd do the same thing here. We would still have an attack of the protonated carbonyl by something that has an oxygen. Here it's water. Here it's the alcohol. There's not much of a difference in its basicity. And it doesn't matter if we have an alkyl group off of this oxygen or a hydrogen off that oxygen. We can still make that attack, have this proton given back to solution, and we get what's called a hemiacetal. But I wanted to draw out that this hemiacetal, it's a new name, is really just like a gem diol. This hemiacetal, half of an acetal. Now this is again where we see we have to use an acid catalyst if we want to make something beyond this. If we want to go further than just the addition product and eliminate off water, we can't use base, because if I use base, I would just abstract the proton and be stuck there or drive off this OR group. That would give us nothing new. We'd go backwards. But if we consider in solution where we still have regenerated that acid catalyst, if that acid catalyst protonates not this oxygen, but this one here, oh, we get a good leaving group. We get a good leaving group, and it's new. Oh, that's even better. It's new because if we protonate this, we can go backwards to something old. But if we protonate the OH, we protonate that, then we get something new coming off, and we get an intermediate that's positively charged. Intermediate that's positively charged. This oxygen has helped push off the water as a good leaving group. And we can get a second equivalent of the ROH to come in and attack, lose a proton, and we get the full acetal. You like that? Well, let's go ahead and look at that in a slow motion. We'll draw out the full mechanism for this, what we call acetal formation reaction. This acetal that we have on the right still has this instability that's often seen with addition products. We had said in the early part of this discussion, we had said, and skipped this slide, that addition products are hard to stabilize. The steric effects are such that these R groups, along with these OH groups, create a little bit of a steric hindrance around this carbon that's tetrahedral that limits the addition products that we can have to a ketone. They tend to give us unstable products. These addition products are usually a little higher in energy than the starting ketone and aldehyde. The exception being electron withdrawing substituents as R groups already being on the ketone or aldehyde. So electronic effects, ketones are more stable than aldehydes. Ketones can even be harder to make addition products with than aldehydes. So in general, the conclusion is when it comes to addition products, really the only thing that's favored energetically is the few unbranched aldehydes that react with nucleophiles. So if we have an unbranched aldehyde and the addition of water, alcohols, things that can, if we have reversibility, things that react with unbranched aldehydes tend to give us more stable products. So as we look at this ketone, for example, the ketone, this is not an aldehyde. We have then some steric repulsions between groups here around this tetrahedral carbon, and it'll want to walk backwards. The way we can fight against that is to take off the water, have a lot of the alcohol, so we can remove the water that's formed as a elimination product. We can try to remove that water from the reaction to drive this reaction by the Chatelier principle. Let's go ahead and look at this mechanism in slow motion. So let's go ahead and go through this mechanism in slow motion. So I'm going to go ahead and draw the ketone, and again remember, just starting off, that if we have a ketone and we're considering, I'm just going to draw the reagent above and have the catalyst below here. Oops, I think I made too many. So I should have just two carbons here. There's my dial. Apologize, the dial's got two carbons here. We'll just try to clean that up a little bit. And we have the catalyst. Now let's remember that if we have an alcohol, a diol, reacting with a ketone, the addition product's not going to be favored thermodynamically. We'll have to drive it by the Chatelier's principle because there's reversibility in these reactions. So we would protonate the ketone. That would be first. The acid catalyst get it involved in the first step. So we're going to show protonation of the ketone. I didn't show that mechanistically, I just went ahead and put it on. Now we would have the oxygen in the diol can attack the carbonyl. It's not very basic on its own, but with protonation of this oxygen, we can have this weak nucleophile or weak base come in and attack. So we've done that, and I'm going to show it to the bottom right. I'm going to have my methyl groups over here. I'm going to show that oxygen on the right here, and we have our OH here. This would be our hemiacetal, because we're at that point where we have initial addition, I should say hemiacetal in the protonated form. We have the hemiacetal because we have the addition of that one of these oxygens to the carbon. This would still have the instability that we have with all addition products, but it wouldn't be a full addition to make an acetal. It wouldn't be an acetal because we still have the OH from the oxygen of the original carbonyl. We have that in the OH form. So now we're going to do a PT, that's a proton transfer, to make this a good leaving group. We have a good leaving group now. If we do a proton transfer the catalytic acidic proton to this OH group, we can drive it off, lone pair to pi, sigma electrons back to lone pair for this oxygen. So we've driven off this water, so I'm going to just say plus water. Now this is key. If we want to drive the reaction, that water that just came off, we can use what's called the Dean-Stark trap, this reaction going in a sort of a distillation state, where this can be removed through a distillate to remove that oxygen from the reaction solution. Now we can have, oops, I forgot something. If I come down with that lone pair, this has to be positively charged. Well, that's going to set up our next reaction. If this is positively charged, I hurt, this carbon hurts. So if we bring down the lone pair, this oxygen becomes positive, this carbon also becomes very reactive. So we can come back around 1, 2, 3, 4, 1, 2, 3, 4, 5 membered ring. We can do that. We can have 5 and 6 membered rings fairly easily. We can come in and attack and drive those electrons back up. So now I'm going to switch to having these down to the bottom left and bottom right. I'm going to have this oxygen here on the right, and the new oxygen that just came in is here on the left. Still has that proton. This is going to be our source actually of the catalytic proton that we give to the solution, back to the solution, so this can all run again. So if we lose that proton, you say, well, who do you lose it to? Just wherever it was in the beginning, the solution, the aqueous solution, catalytic proton. We're going to give that back to solution, and we now have the full acetal. This is again just an addition product, much like the hemiacetal was. That I should have had double-headed arrows here. We can revert, or not double-headed arrows. Should have equilibrium arrows. Saying this whole thing is reversible. So to drive the reaction, we wanted to have the distillate with toluene of this water with benzene. We wanted to distill this off in a Dean-Stark trap so that we can drive the reaction to the full acetal, because this is all reversible. And the acetal is not as stable as the ketone in most cases. In the case again of an unbranched aldehyde going through a reaction with the diol here, we could maybe have some favoring of the acetal. Well, that's it. That's a mouthful here. So you may want to walk through this a couple times to know how we can form from a vicinal diol. This is a vicinal diol, meaning the OH groups are off of adjoining carbons. How we can make from a vicinal diol and a ketone or an aldehyde with a little bit of acid added, sprinkled in, we can make acetals. You may want to go through that mechanism. It's a very common reaction in organic chemistry courses, and it's one that you should know. Our last reaction we're going to consider is the reaction with amines. Now, important to point out that amines have a little more basicity than these oxygens in the diol, the alcohol, and water. They have a little more basicity. Therefore, they have a little more reactivity. They don't necessarily need to have a catalyst for this first step. So if this nucleophile is an oxygen, we need to protonate this oxygen in the carbonyl. But if this nucleophile is an amine, we can have a significant amount of an attack of this carbon without protonation of the oxygen. So I'm going to show that in these slides as attacking without protonation. Many books will show the protonation before the amine comes in. Maybe it's 6 one way, half a dozen the other. So let's just go to the balanced reactions first of amines, either primary or secondary, reacting with ketones or aldehydes. Let's take the primary amines. Primary amines are amines that have one alkyl group off of them, not two. They have two hydrogens. This is important. If they have two hydrogens, what we can have in the end, if we're going to our imine, these two hydrogens come off with this one oxygen to give us what's called an imine linkage, a CN double bond. If we have a primary amine and a ketone or aldehyde with a little bit of acid catalyst, we can make what's called imines, CN double bonds, and we kick off water. So we may again want to try to drive the reaction. Since this is reversible, we may want to drive it by capturing the water, distilling it off, I guess pushing this by removing the water. Now if we have a secondary amine, meaning two alkyl groups and only one hydrogen off the nitrogen, we don't make imines. You can't. There's not two protons to remove. We have to keep those two alkyl groups on the nitrogen. And what we get is what's called an enamine next to the nitrogen, and involving the carbon in the original ketone, we have a double bond back to the carbon that was in the carbonyl. It's a little more complicated. Just remember, if it's a secondary amine, just remember we go to enamines, not to imines. Wherein the double bond is formed between the carbon and the original carbonyl that's connected to the oxygen and one of the alkyl groups. That's called an enamine. Now I'm going to show a partial mechanism, and then we'll go to the full mechanisms for these and we'll be done. So the partial mechanism goes something like this. If we have an amine, and I'm just going to leave it undefined, well, I guess we'll use a secondary amine. Has two R groups, a hydrogen off of this nitrogen. We haven't defined what those R groups are. The nitrogen can make the attack. We can protonate this oxygen. We can have a second protonation of this oxygen. That should be shown here because we want to lose water. We can have a second protonation. So we can protonate this oxygen not just once but twice. And if we protonate twice, we get water as a leaving group. We get our aminium ion. If this was a secondary amine, we can't lose those two R groups. We can lose one hydrogen, and we could lose that. But we don't have a second hydrogen to lose. This is called an aminium ion. Now, if it was a primary amine, we'd have two hydrogens. We could just take off a hydrogen from this, what's called the aminium ion. But in the aminium ion, if we have two alkyl groups, we have to find a different way to relax the energy and come back to a neutral structure. We have to go to enamine. So this addition elimination is part of every imine-enamine reaction, but it's just how you end in that elimination reaction. You drive off water in the elimination reaction, but if we end with an aminium ion where we have alkyl groups, then you go to the enamine. If you have an aminium ion where you have one of these as a hydrogen, you just go to the imine. I think this will make sense as we go into the particulars. Let's take a primary amine. We said we could attack without protonation. We can get a fast PT because this is in the zwitterionic state, and we can go to something like what we saw in the hemiacetals, the hydrates of aldehydes and ketones. We have a tetrahedral carbon where we've just basically absorbed in this case, we've absorbed in the nitrogen and the two hydrogens with it. And this should be a primary amine, so I'm going to turn one of these hydrogens into an R group. That should have been a primary amine, so we're just going to take this whole thing and just add it in. We've added it into the carbonyl. So we've had an addition reaction. And we've taken one of the hydrogens and put it on this oxygen. Now this is where the catalyst has to come in. The catalytic protons, we have to create a good leaving group out of this oxygen. We need to make water. So if we do that, we have a good leaving group with the OH in this carbonyl amine, which is like a gem diol, and it's what we've seen before. It's just like the gem diol, addition of water to a ketone. Well, this is addition of amine to a ketone. So it has the same instability. But we can protonate this oxygen just like we did with the gem diol-like structures for alcohols, the hemiacetals. We can absorb a proton, make a good leaving group, drive down the lone pair, make a pi bond. This is our aminium ion that we talked about is so important. This is after the elimination of water. We get an aminium ion. And from this point, since we had one of these be an R group, we're going to stay with that. This is still an R group up here. Oops, let's leave that as a hydrogen and make this as the R group, because we're going to take in the last step for the formation of imines. We take a proton from the nitrogen that's positive because he has one. We have one left. He had two to begin with. We took one and transferred him early. We now take another one and pick him off with the water, and we get our imine. So you want to just know this reaction. I don't know if you'll necessarily need to know this for be able to reproduce it, but just to understand, this is the key sort of point in determining whether you have an imine or an enamine, because in this reaction with having two hydrogens, we can tear the last one off from the aminium ion and make the imine. But if we get to that same point, going through a very similar reaction, getting to a carbonyl amine, addition of the amine, and here we have no more protons. We can still protonate the oxygen in the OH group, have that eliminated off. We get to the aminium ion, and we have no more protons. So there's nobody we can tear off that's directly bonded to this nitrogen. So we have to go after the alkyl groups that were in the original ketone. We go after their protons, have an elimination reaction of sorts. It's like instead of breaking off completely, we have, in a sense, we take a proton next to the leaving group. This can kind of be considered as a leaving group, except that the only thing we're doing is breaking a pi bond, not a sigma bond. So we take the proton, make a pi bond, and don't eliminate off a nitrogen or like a halogen coming off. We just break a pi bond back to the nitrogen. So it's as like an E2 reaction you've seen in OChem 1, but the only thing we break on the other side is a pi bond. So we have the formation of our ene, and we have our amine, so we have an enamine. Well, that's it. It's a long journey that we've taken through a lot of reactions. Don't forget these two things. That one, a lot of our addition reactions are unstable. So these four really give us unstable products that we can't have reversibility back to the starting reagents. So a lot of the times the reactions have to be driven by Le Chatelier's principle, either something precipitating out of solution as product, we take off water. We have a lot of reversibility with these four reactions: water, alcohol, diols, and amines reacting with ketones or aldehydes. Much of it's caused due to, at least in the case of addition products, the alcohols and the diols is because of this instability of the gem diol. So in very rare cases do we have a starting energy for the ketone or aldehyde that's higher than the diol, or sorry, the addition product. The acetals and such are a little bit usually higher in energy, and we have reversibility back that can be a problem. That's it. Bye-bye.